welcome to the Explainer. Today we're talking about NumPy. It's the library that's quietly powering almost all of Python's data science capabilities. And look, if you've ever touched data in Python, you've already used NumPy, probably without even knowing it.
So, before we even get into what NumPy is, let's talk about why it even exists. I mean, Python already has lists, right? Why aren't they good enough for heavy-duty data work? Well, it really comes down to two things: speed and simplicity.
All right, here's the game plan for today. We're going to start with why NumPy was even created. Then we'll look at its core, the array. After that, the real fun begins with array manipulation. We'll touch on why it's so fast and powerful, and finally, we'll wrap up with your first steps.
Okay, let's get right into it. The difference between doing math with a plain Python list versus a NumPy array, well, it's like trying to tell 1,000 people something one by one versus just making one announcement over a loudspeaker. And this says it all, really. On the left, that's how you'd add two lists in Python. You have to write a for loop, you go through element by element. It works, but it's clunky. And for big data sets, it is painfully slow. Now, look to the right. That's NumPy, just A plus B. It's not just that it looks cleaner, it's wildly faster.
So how is that possible? How does NumPy pull off this magic trick? Well, the secret, the absolute heart of it, is this thing called the n-dimensional array, or ND array for short.
So what is it? Just think of it as a supercharged grid of values. But here's the key, the secret sauce. Every single thing in that grid has to be the same type, all integers or all decimals. This rule is what lets NumPy blast through calculations on the whole grid all at once.
And getting started is honestly super simple. You just import NumPy as NP, that's the convention, and then you can take a regular Python list, even a list of lists like this one, and turn it into a powerful NumPy array with just one command.
Right? And once you've got one of these arrays, it's not some mysterious black box. You can ask it things about itself. You can ask for .ndim to see how many dimensions it has, our last one at 2. You can check its .shape to see its size, 2 rows by 3 columns. .size tells you the total number of items, and .dtype tells you what kind of data you're actually dealing with. Super useful.
Okay, so we've got the basic building block, the array. Now for the fun part. Let's see what we can actually do with it. This is where NumPy really starts to feel like it has superpowers.
First up, this concept called vectorization. The slide says it perfectly. Give one command to the whole army. Instead of looping through and telling each number what to do, you just issue a single command to the whole array. You say a times 2, and NumPy instantly understands to multiply every single element by 2. No loop needed.
And that leads us to another really clever trick called broadcasting. Let's say you want to add just one number to an entire array. Well, NumPy is smart about it. It effectively stretches or broadcasts that single number across the whole array so the math just works. It lets you combine arrays of different shapes without writing a bunch of complicated code.
Oh, this is one of my favorite features. It's called Boolean indexing. You can literally ask your data a question. In this case, we're saying, hey array, which of your values are bigger than 2? That a greater than 2 part creates a temporary mask of trues and falses. Then, when you apply that mask back to the array, it only gives you back the numbers where the answer was true. It's an unbelievably clean way to filter your data.
Okay, so we've seen a bunch of the cool tricks NumPy can do, but let's zoom out. Why is this so important? Why is it literally the foundation of pretty much all data science in Python? Why does it matter in the real world?
So what's the big secret? Why is it so much faster than just using Python lists? It's not just a little tweak. It's a completely different philosophy under the hood, all about how it talks to your computer's hardware. I like to call it the speed trifecta. There are 3 big reasons. First, the heavy lifting in NumPy is actually done by code written in C, which is way faster than Python. Second, those vectorized operations we talked about avoid all the slow overhead of Python loops. And third, and this is a big one, NumPy stores its data in one continuous block of memory. This lets your computer's processor grab huge chunks of data all at once and process them in parallel, which is a massive speed boost. And because of all that speed and power, NumPy is everywhere. It's the bedrock that so many other famous libraries are built on. Think pandas, scikit-learn, even TensorFlow. It's the engine behind machine learning, complex scientific simulations, financial modeling, and even image processing, because what's an image really but a giant grid of numbers? All right, you get it. NumPy is powerful. So how do you get started without tripping over some of the common pitfalls? Let's talk about a few best practices to get you going. Okay, rule number 1, and this is a big one. If you're doing math, use arrays. Just don't use Python lists. Second, always try to think in a vectorized way. If you start writing a for loop, stop and ask, is there a NumPy way to do this? Third, a heads up. Sometimes when you slice an array, you're just getting a view of the original data. If you change the slice, you change the original. So if you need a totally separate copy, make sure to use the .copy method. And a final pro tip. Working with huge arrays, you can save a ton of memory by telling NumPy to use a smaller data type, like a 32-bit float instead of the default 64-bit one.
So there you have it. For making crazy math simple to making your code run, 100 times faster, NumPy is the tool. It really is the engine that drives so much of modern computing. The only question is, what are you